Welcome to Olympian. I am Aditya and I am all of 18 years old. And today we are going to be discussing about generation and conduction of nerve impulses. Now, before we begin the lesson, since it's my first video, a little background on me, a little about myself. I graduated class 12 this year from Don Bosco School, Park Circus, Kolkata. And at the risk of sounding immodest, I am laying out my academic achievements, my academic qualifications before you. I am an NTSE scholar, a KVPY fellow, a JBNSTA scholar, and I was selected to represent India at the International Biology Olympiad this year, having secured an All India rank of 5 in the Indian National Biology Olympiad. An opportunity that I could not take, unfortunately, because the dates for IBO were clashing with the date for my NEET examination. But that's fine, and technically I should be in college by now, but the results of the NEET examination are not out yet, and hopefully I can convey some good news soon. Okay, that's enough about me. Now let's move on to the lesson. Okay, now before we delve into the actual process of conduction and generation of nerve impulses, I'll just elaborate on the basics a bit. Okay, the basics. And by the basics, I mean, let's talk about ion channels. Now, ion channels, these are a category of transmembrane proteins. Transmembrane. Now, hang on a minute. What does the word transmembrane mean? Like, it's such a long word, right? Isn't it? And it seems like some sort of medical jargon or maybe some sort of biological jargon, which makes us all hate biology, isn't it? Most of you who hate biology hate it because there's an abundance, there's a plethora of these long words, and you just can't seem to get it in your head, right? It's very easy. Trans means transecting, going through. Transect or go through. And membrane, of course, is the cell membrane. It refers to the cell membrane. Alright? So basically, if you remember the structure of the cell membrane from elementary discussions, maybe bio classes at school, and this is the phospholipid bilayer composed of hydrophilic heads and hydrophobic tails. I'm sure you remember what those are. And this is a protein. It's going through the membrane. See, it's going through, right through the membrane. This red line signifies the midline of the membrane. I'll just draw some more phospholipids on the other side as well. And you see the protein is going right through the membrane. It doesn't care that there are phospholipids there to stop it. These are just puny tiny soldiers, and that is a large troll, a large mountain troll going through the puny hobbit army. Alright. So the hobbits were more powerful than the trolls, but anyway, the hobbits turned out to be victorious in the end. But anyway, let's just consider that these are puny tiny hobbit armies, and this large blue thing is a mountain troll that's just going right through them. Okay, and this is what we call the transmembrane protein. Okay, so ion channels, they are a specific category of transmembrane proteins, and in the fact that they are pore forming. So they form pores across the membrane. They form pores across the membrane, allowing ions to pass through. Okay, now ions, as we know, they are polar, right? They are polar, and they are hydrophilic as such. And the phospholipid bilayer, if you remember, it's hydrophobic. The phospholipid bilayer is I mean, the phospholipid bilayer isn't hydrophobic as such because it's a bilayer, isn't it? It's composed of hydrophilic heads and hydrophobic tails. But the tails on the inside, they're hydrophobic. Now, if there's an ion, suppose it's an ion that's coming in, let's say it's a positively charged ion. The hydrophilic part, it's all fine with it. Nah, it's cool. You can go in, man. No problem. But once it comes to this hydrophobic part, this is like a gatekeeper. No, no, you get out of here, get out of here. It just kicks it out. It's not, you're not allowed to pass. This is my domain and you're not allowed to go through it, okay? So the hydrophobic part does not allow it to go through, does not allow the ions to go through. Now the cell's in a dilemma, right? What's it going to do without those ions? It needs these ions for its own survival, and its own membrane is not letting these ions pass through. That's sort of the biggest treachery, the biggest treason in the world, right? It's treason then, in the words of Chief Palpatine. That was a bad joke, tough crowd, huh? But yeah, so essentially what it needs is for, let me change the color of my pen, is for these guys. See, this is one side of the protein. This is how they are depicted basically. They don't really look like this, but because they are molecular, really tiny, and these are like models to help us better understand. And if you see, there's a pore right to the center of it, isn't it? And the ion it can pass right through that pore, and the ion is happy now. The ion is happy now. It's passed right through that pore, and the cell is also happy now because it has got those ions that it needs. Okay, so yeah, so that's basically the function of the ion channel, allowing the ions to pass through. So that was about the function. Let us talk about the classification now. Classification is very important. And ion channel. Now there's a lot of different classifications. If you browse the internet a bit or maybe go through a couple of books, you'll see there's a lot of different categories people speak about, and it's like it seems never ending, inexhaustive, right? So I'll just classify it into the three main categories, which, in my opinion, are the main. You may disagree, but let's just see. We don't need to delve too deep into it, but I'll just tell you a bit about the. Since we're talking about the basics, I'll just tell you a little bit about it. Okay. So the first category, which is going to be important, going to be the most important to us in our present discussion, is voltage gated ion channels, right? Voltage gated. I'll just make a sort of cloud around it to signify its importance. The second category is ligand gated. Now, what are ligands? It's simple, really. Ligands are actually chemical molecules. It's sort of like a hand that fits into a glove, right? Or a piece of a puzzle that fits into another piece. So the ligands are chemical molecules that fit into their specific co-molecules, you can call them, known as receptors, and they cause some sort of structural conformational change in the receptor, and that leads to a cascade of sort of things happening, and the cell gets all excited and all, and so that's basically the function of a ligand. And so hang on a minute, yeah, the ion channel can be ligand gated as well. It's not of real importance considering our present discussion. Voltage gated is of the most importance, but I'm just telling you about it. And the third one can be mechanical. It just opens and closes by mechanical means, nothing too exciting about it. But the voltage gated ones, these are really interesting. Okay, these are controlled by changes in potential difference across the membrane. Now, how the potential difference arises across the membrane is a different story altogether, and I'll come to it in just a few more minutes. But for now, just trust me, okay? Just trust that I am telling you the right thing, and know that it is controlled by changes in potential difference across the membrane. Okay, I'm not going into ligand gated and mechanical because it's not of much importance now. Perhaps in another video I'll delve into that. And in voltage gated ion channels, I'd just like to talk about a particular type of voltage gated ion channels called the sodium ion channel. Sodium ion channel. Now, these guys are really peculiar. Okay, if I'll just draw the basic structure of the ion channel first. This is the ion channel, and if you look at it, you'll see it's open at both ends. Right now, that's not of much use, is it? These open at both end ion channels are also prevalent in the cell. They are called leaky channels. They are called leaky channels. Leaky, Leaky, leaky channels, and they have their own uses. Like you'll see in a minute that potassium leaky channels are very important. But for now, for sodium ion channels, leaky channels are not of that much importance. And so there is one gate here. In the initial stage, this gate remains closed. Okay, and this is called the fast gate. All right, now you'll get to know why it's called the fast gate in no time. I'll tell you about it, but for now, just roll along. Okay, and this gate initially remains open and is called the slow gate. Every term has a context, a meaning, and it's just not there because whoever whoever came up with this needed to put some terms there. It's got an etymology, and why it's used in that particular context you'll get to know very soon. So, but for now, just roll along with it. Okay. So yeah, that's the sodium ion channel, and that's perhaps the most important ion channel in the context of our present discussion. And now let's go to the basics part 2. Let's talk about uh, a normal human cell, any cell of the body. I know you must be thinking, hang on a minute, how does that work? We're talking about nerves, right? How can any cell of the body work? But we are first gonna, before we start talking about nerves, we've got to talk about the other cells, right? That's just how it works. If it does not make sense to you, it will. All right, so we are back to the basics. CONTD. Okay. Uh, I think orange is a good color for this one. I am drawing a cell. This right there is a cell. Okay. I've left some space empty there. That's for a very important bit that I'll come to in a minute. But first, I'll make a nucleus as well. Yeah, that looks more like a cell now. So let's first get our directions right. Every sailor, every navigator has got to have a set of coordinates, right, in order to tell him where he exactly is. Otherwise, he'll just be lost at sea. And if we do not lay out our directions with respect to the cell as well, there'll be a lot of miscommunication, a lot of confusion. Like what part of the cell am I referring to? Is it the top? Is it the bottom? What do you call the top? What do you call the bottom? It's very simple. Okay, this part, this is called the basal part. This is, since this is the base, the word comes from base. Okay, base, and it's called the basal part. These sides, they are called the lateral part. Lateral, lateral, and the top we arbitrarily set up, not arbitrarily, it's actually defined. The directions are defined by what is present right here. Okay, I'll come to what is present right there in a minute. And this is called the apical part. It comes from apex. Like in a triangle, if you remember, we have a base, then there's the apex, isn't it? So it's just like that. This is the apex and this is the base. I'll just remove the triangle. It's not of much use here. Alright, and what I'm about to write is very important, and what I'm about to say is also very important, so listen very carefully and watch very carefully. This is one of the pillars of biological science, of human physiological science. Okay, every cell of the human body has a sodium potassium ATPase pump on its basolateral membrane. Get this statement absolutely engraved into your brain, alright? Every cell of the human body has a Na plus K plus ATPase pump on its basolateral membrane. This is one of the pillars of human physiological science, of human physiology. Okay, and I'll draw the pump right here. Okay, so let's just zoom in and see what that pump does. Okay, the pump is a protein in itself. Phospholipid, 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 phospholipid. Okay, this is the pump. Now, essentially, I'll just complete the phospholipid on this side as well. Just two of them should suffice. Essentially, what this pump does is it takes three Na plus ions which are present inside the cell. This is a cytosolic site, the cytosol inside the cell, and it throws them out of the cell. It just kicks them out. It just boots them out. There's these guys, they have no prestige. They don't have any self-respect. They get kicked out of the cell wantonly, left, right, and center. Okay, and they just get, this is a very bad rendition of a boot, but anyway, they just get kicked out of the cell. 3Na plus, they just get kicked out of the cell. Very sad little guys. But anyway, that's how the world works, right? And on the outside of the cell, this part is the cytosolic part, so this has to be the outside, right? There are two K plus ions, right? Now these guys, they are very well respected guys in society, all right? So they get brought into the cell. They get brought into the cell. They get brought into the cell and they are very happy. And the Na plus guys, the three Na plus get thrown out of the cell, and the two K plus go into the cell, and that's just how it works. Okay, and there's another, like for every transaction there has to be a currency, right? The currency in this case is ATP, adenosine triphosphate. That's basically the energy currency of the cell, if you remember. So the pump takes ATP and it throws out three Na plus molecules, and it takes in two K plus molecules, and it continues doing this throughout its lifetime, right? This pump never stops, and it makes up a really huge amount of the ATP that we generate through respiration. It accounts for a very major amount of that. That's like one of the reasons why we, even if we lie around in bed all day, we need to have a minimum intake of some few thousand calories, right? It's basically one of the major reasons for it is the sodium potassium ATPase pump, because it keeps on working, it keeps on taking ATP, it keeps on throwing 3 Na plus outside and takes in 2 K plus inside per cycle. So it constitutes a very major part of the basal metabolic rate of a human being, and it's very, very important in the context of our present discussion. So get this into your head straight. Okay, 3 Na plus ions get kicked outside and 2 K plus ions get pulled inside per cycle of the sodium potassium ATPase pump. Now I just want you to think about it a bit. Okay, I don't need to redraw the cell. I already have the cell right here. So if all the Na plus gets thrown outside, the red guys are Na plus, and all the K plus gets pulled inside, what do you think happens? What do you think happens to the concentration gradient? Right. Uh, if you consider the concentration gradient of K plus, there's much more of them inside, right? More inside. And there's very few K plus outside. Like it's very negligible, right? Since all the K plus is getting taken in. I'm sorry. Since most of the K plus is getting taken in, there's very few of them outside, right? The opposite is the case for Na plus, of course, because Na plus is more outside. They're getting thrown out. They're getting kicked out left, right, and center. So there's more outside, and there's very few inside. So there's a concentration gradient. Let me show you how that works. Let's say purple is for K plus, as we've been working on it so far. So the concentration gradient of K plus is directed outside, right? The base signifies where there are more K plus ions, and the head of the arrow signifies where there are less K plus ions. So the concentration gradient is directed outside, more K plus to less K plus, right? The opposite is the case for Na plus, of course, as you can understand. Uh, there's more Na plus and less Na plus, right? So we've got the basics straight. Now let's move on to a more specific type of cell called the nerve cell. This is what you've been waiting for, right? To talk about the neuron. Yeah, we want to be neurologists. We want to talk about neurons. Okay, so let's talk about that. Let's talk about neurons. Okay, neuron, a fascinating field of study, isn't it? Neurology. Everybody wants to be a neurologist. Okay, so let's say this is a nerve cell, and I can literally see the disappointment on your faces, right? Because like, what sort of a nerve cell is this? I was expecting to see that sort of, it's got a head with a sort of Medusa sort of head with dendrites and all, and an axon and myelin sheath, and the head is the body is called the cyton. Wow, these are such interesting words, right? I'll come to that. I'll come to that. Don't worry. But let us first take this useless, this worthless schematic diagram. It's not worthless. It's actually very important for the sake of understanding. But let's just take this for now, and I'll draw the all important sodium potassium ATPase pump here, basolateral side of the membrane, and I think we'll just go from here, right? So yeah. Now, if you remember what we talked about last time, is that there's a large amount of K plus inside, K plus, and a very large amount of Na plus outside, Na plus. They're separated by this barrier. They want to meet, but they cannot because they're separated by a barrier, right? And the concentration gradients, I'll also lay those out. K plus concentration gradient directed towards the outside, and the Na plus concentration gradient directed towards the inside. Okay. Okay, so that's that then. That's that's all about what we talked about in the last slide. Now I'll just make a small cut in the membrane here, and I'll insert a channel. Now this channel, as you can see, it's always open, right? This is a, what is it? It's a leaky channel. Okay, this is where the leaky channel comes into play, right? And this is potassium leaky channel. It leaks potassium ions. It's leaky, right? It's leaky. It leaks potassium ions. That's its significance. Now, since potassium is more inside the cell, it needs to go outside the cell. K plus inside to K plus outside, right? So potassium, there's no such respite for sodium, right? It does not just come into the cell, but this has significance. Potassium going outside the cell. So as you can see, since there are three Na plus ions going outside and two coming inside every cycle, now you can already sort of gauge like what the difference is. I suppose it's by one charge, isn't it? So like it's like positive charge is accumulating outside. Positive charge is accumulating outside, right? And the inside is less positive. It's got K plus ions, right? That's also positive charge, but there's just two of them for every three Na plus outside, so it's less positive, right? So what do you think about the potential? The potential is more on the outside, less on the inside, right? So can we say that the inside is at a negative potential compared to the outside? Yeah, we can say that. That's just elementary physics, right? Plus, in addition to that, there's K plus ions going outside as well through the leaky channel. So K plus inside is decreasing. It's not 2 K plus for every 3 Na plus anymore. It's less than that, right? It's going outside. Plus, there's one more thing. There's one more important component to this, is that there are proteins inside. Let's say that is a protein which are negatively charged. Negatively charged protein. Negative protein. Okay. So that's also increasing the negativity on the inside. So a point comes when this K plus stops going outside, because the inside is the negative proteins also pulling it back inside, right? There's an attraction to the negative proteins. It's a positively charged ion, and when this attraction sort of counters the concentration gradient, right? So point comes when all of it is in equilibrium, when the potassium going outside, uh, I'm sorry, potassium going outside through leaky channels stops. Okay, there's a point at equilibrium when the K plus concentration gradient is countered by repulsion from positive charges on outside and attraction from negative proteins inside, right? So if you see the general trend here, the inside seems negative, right? And the outside seems positive. So there is a potential difference directed along this direction. I call this let's take a different color. Let's take light blue. This is a potential difference that's directed to the inside of the cell. So we say that the inside of the cell has a negative potential compared to the outside, alright? So the inside of the cell has a negative potential compared to the outside, and this negative potential inside the cell is called resting membrane potential. Now, every cell has a resting membrane potential, and it's more or less equal for every cell. But since we are concerned about neurons, I'll tell you the one for neurons. The value of the resting membrane potential for neurons is approximately minus 70 millivolt. Okay, this is empirically derived. You can also derive it using a few basic calculations using the Nernst formula, but it's not really required. It's about minus 70 millivolts. All right, the negative potential inside the cell. So you can see there's a potential difference. I talked about a potential difference earlier when I was talking about voltage gated ion channels, and this is the source of the potential difference, and it's of huge importance. If you can just look at the implications for a bit, this implies that the cell is always polarized, right? It's always polar. It's polarized. It has a positive polarity outside and a negative polarity inside. So it's always polarized. Okay, and this polarization is very important for the property of neuron, which is excitability. Okay, neuro excitability. Now, let's move on to the next slide, and we'll talk about neuro excitability. Okay. Okay, so now let's continue talking about the neuron. Neuron, CONTD. Okay, and in the last slide I told you that I would talk about neuro excitability, and let's do that. Let's do that. Okay, let's go to it step by step, one by one. Okay, I'll redraw the bare bones schematic of the neuron, which I'm sure you have come to appreciate by now, though I don't think you like this picture as much as that cool one with the tentacles in the head and all. And let's draw the pump right here. Okay, and I also drew another channel which I call the leaky channel, right, if you remember, in purple. And we have already established that the resting membrane potential RMP equal to minus 70 millivolt, right? So there's a charge of minus 70 millivolt. It's not, I'm sorry, it's not a charge, it's a potential of minus 70 millivolt on the inside and 0 on the outside. This is what it means. It may not be, the values may not be exactly like that, but it's a difference that matters, not the exact values, right? And that looks bad, kind of. So I'll just rub it out and yeah. So let's say there's a potential of minus 70 MV on the inside and it's 0 MV on the outside, right? And now I am coming to a very important part. Let me insert a few more ion channels in here. And if I remember, I use green, right, for the sodium ion channel, because that's what I'm putting in here. And that's the key to all our troubles. Here's the channel, and if you remember, the fast gate that's on the outside, the fast gate is on the outside, that was closed initially, right? And the slow gate on the inside, it was open initially. I'm sorry. So this is the sodium ion channel. Let us put in one more ion channel in here, and this let's make it in red. Okay, this is the voltage gated potassium ion channel. I haven't told you about this before, but even this thing right here, it's a slow gate. It's not a fast gate, it's a slow gate, and it does not have the second gate like the sodium ion channel does. It just has a transmembrane protein, the transmembrane porous protein, that is the actual ion channel, and a slow gate on the outside. And this is for potassium ions. I'll just label them right here. This is the Na plus channel, and this is the K plus channel. This is the K plus leaky channel, and this is the Na plus K plus ATPase pump. Okay, now we are ready to start talking about what actually happens. Okay, so I'll do it graphically. All right, I'll make a kind of a big y-axis right here and an x-axis right here. Okay, let's label the axes. It's very important we do that. X, O, Y, Y dash. Now let's say this O is at 0 millivolt, and the y-axis represents the potential difference in millivolts, and the x-axis represents the let's say the profile of the sketch. Okay, I'll not label it. I'll keep it as it is. Okay, you'll come to know why that is in a minute. And if you remember, the RMP is minus 70 millivolt. Okay, this is the RMP. Okay, and I'll draw another line across the RMP right here, parallel to that, and let's make it a dotted line. All right. All right. So, and one more line. You'll understand the significance of this line later when I actually talk about. Let's make it in turquoise, right? Let's make this line around. It'll be around somewhat around here. It's not exactly accurate, but that's fine. Okay, and I'll make this line dotted as well. And this line, it's going to be at minus 55 millivolt approximately. You'll get to know why I chose that value in a moment. Okay, now we are ready to begin, and let's begin from the beginning. As most good novels say, as most good teachers say, let's begin at the beginning. Okay, so this is the membrane, and I'm not making the potassium channel right now, the potassium voltage channel. I'm just making the sodium channel. Okay, this is the sodium channel, and its fast gate is closed, slow gate is open, as I told you. Okay, and now there are these potassium ions outside, right? I'm sorry, these sodium ions are outside, right? Sodium. Now let's say there's some sort of, maybe you get hit by a hammer or something, or maybe somebody touches you. So let's say there's some input of energy, that may be mechanical energy, electrical energy, heat energy, whatever, just some stimulus acting on your body. Let's say somebody pricks you with a pin on your skin. That's mechanical energy, right? Mechanical energy is imparted. Now when mechanical energy is imparted, the sodium ions, what they do, a few of the sodium ions go inside go inside the cell. They cross the it's a repulsive barrier, right? The hydrophobic part of the phospholipid bilayer, it acts as a repulsive barrier against the Na plus ions entering inside. But if you see the concentration gradient, it's directed towards inside, right? Like the Na plus wants to get inside, it just cannot, because there's some it does not have enough energy to cross this repulsive barrier. But once it gets that energy, it doesn't care about the fact that there's a repulsive hydrophobic part inside the phospholipid bilayer, and it just goes into the cell. It does as it wishes. All right. So initially, if we draw the profile here, I'll do it in red. If I consider the profile here, it's at minus 70 initially, right? It's at minus 70 initially, and then the sodium is getting inside. So the inside is, what's happening to the inside? The inside is at minus 70. But once But once the positive ions get inside, it's increasing, right? It's becoming more and more plus, 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 because it's the Na plus ions that are getting inside, right? It's getting more positive. So if you consider the profile here, positive is towards the upper side. So from minus 70, let's say it goes to minus 69, minus 68. It's getting positive, it's getting positive, it's rising. Oh yeah, now this is what we want to see, right? It's rising, it's rising, it's rising. Such suspense. This is the moment of the climax, right? And what happens? Nothing. Oh my god, that's so disappointing, right? Oh my god. After all this work, what do we get? Nothing. It just goes back to what it was, minus 70. Like, that's got to be the biggest cliffhanger right there, right? That's got to be the biggest cliffhanger right there. Okay, let's try again. Let's try again. I can sense the disappointment in your faces. I can sense the disappointment that you're feeling. I'm disappointed right now too. All right, and let's try again. Let's try again. Okay, this time let's try something more drastic. Let's try something a little bit more drastic. All right. I redraw the sodium channel, and let's increase the amount of energy that we are hitting the cell with. Okay, let's increase. Let's make this a bold sort of energy, right? Energy. Okay, and I'm hitting it hard with that energy. Okay, and the sodium ions, they are all excited. They're very strong, and they just want to go in the cell. They've got a lot of energy, and they whoosh just go into the cell. Whoosh, they just go into the cell. Now what? Now, if we consider the profile, see, it's back to minus 70. Now it's increasing, it's increasing, it's increasing. There it is. It reaches minus 55. That's what I'm talking about, right? Now that's the real deal right there. This minus 55, it's got a very nice name, right? It's called the threshold potential. The threshold potential. Once it hits that minus 55, once the inside of the cell gets to minus 55 millivolt, now that's where the fun begins, right? I'll draw another one of those right here. And this is the sodium channel. My drawing's progressively deteriorating, but I think you can get the picture. This is the sodium channel, okay? And now this has gotten to minus 55, and the sodium ions are all nicely lodged inside, right? So what happens now is very interesting. This fast gate, it was earlier closed, right? If you remember, initially it was closed. Now what happens is it opens. It opens up, and now the ion channel is open on both sides. Now the ion channel, oh my god, now the ion channel is open on both sides. And the rest of the sodium that were outside, rest of Na plus, they get a free entry. This is an open door. Like, they don't have to pay a toll or anything. It's just an open door, and they can just barge right into the party and start dancing and whatnot. Okay, so the rest of the sodium, it just barges inside, right? And this potential now, it increases very rapidly, plus 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 plus, because all the sodium, all the positively charged sodium, which has gotten inside the cell, right? And it's just increasing the potential like hell. Okay, so if I consider the graph here, oh my god, rising, 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 rising. Okay, and now let's say this is not a very fixed value or anything. Let's say it's plus 10 or something like that. Let's draw a straight line right around here, and I'll make it a dotted line. I've made it a dotted line, okay. And let's say this is about plus 10 millivolt. All right. Okay, now all the sodium's gotten inside the cell, right? That's not good. The cell doesn't want that. The sodium wants that. Of course, it wants that. It wants to join the party, but the cell doesn't want that. And what it does is that I'll redraw it here. And where's my green? My green's here. Yeah. So what happens now is that the fast gate has opened, right? It's not done its job of keeping the sodium outside. So now it's open. Once it's open, it remains open. Okay. But now the slow gate must take matters into its own hand. And it was open initially, right? It was open earlier. But now what happens is the slow gate closes. The slow gate closes, and now the sodium cannot enter, right? It's a dead end. It's a dead end, and no more sodium can enter. Let me just write it here. No more Na plus can enter. Okay, and this, let's say it's plus 10 millivolt right here. Okay, so the slow gate is closed. Let me just write it here. Slow gate open in case of the previous one, fast gate also open, right? And in this case, slow gate closed, and now no more sodium can enter. The fast gate remains open. This gate right here, it remains open, but that's not an issue because it's a dead end at the other end, right? The sodium cannot enter anymore. So the graph stops right there at plus 10 in this case. Now we come to the next bit, which is equally important, and I'll draw it here. Now we are shifting our attention to the voltage gated potassium channels. Okay, the voltage gated potassium channels, they were like this, right? And this has a slow gate as well, which remains closed initially. Okay, and there are potassium ions inside the cell. There are potassium ions inside the cell, and these potassium ions, now what happens, since it's very highly positive inside, you've got to relieve that positivity, right? You've got to make it negative. The nerve cell is a very kind of very negative, very downtrodden kind of guy, always likes to be negative, doesn't like to be positive. It's unlike me and you, right? We like to be positive all the time, but the nerve cell, it likes to remain negative on the inside. Okay, so what it does, since the sodium ions are inside, can't help it, bro, we won't get outside now. Okay, let's just show some of the potassium outside, and we'll relieve the positivity that way. We'll add the negativity by throwing the good guys out of the party. Okay, so what happens now is that the slow gate of the potassium voltage gated channel, it opens. The slow gate, it opens, and the potassium ions, they have a free exit, and they leave the cell. Now if you consider the potential gradient, the potassium ions are more on the inside and less on the outside, right? So they will want to get outside because it's a concentration gradient, right? The concentration of potassium ions is more on the inside, less on the outside. It just diffuses out through the potassium voltage gated channel. Okay, and now since the positive charges are going outside, it's minus, 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 and this decreases the potential inside the cell, and this brings the graph down. This brings the graph back down till here, all right? Now the potassium is outside, and we have okay, I missed out that part, but we have very nice, very cute names for these. Okay, let me make it brown. The sodium ions entering the cell through the sodium voltage gated channel, through when both the fast gate and the slow gate are open, this is known as sodium influx. Sodium influx, very important name. Okay, sodium influx. And the potassium ions leaving the cell through the potassium voltage gated channel when its slow gate is open, this is called potassium efflux. All right. Influx is coming into the cell in large quantities. Efflux is leaving the cell in large quantities. Okay. Now, there's another interesting bit that goes on here. Okay. And since the potassium's voltage gate is pretty slow, right? It's lethargic, it's slow. It doesn't want to close even when the resting membrane potential has reached minus 70 millivolt. All right. So it remains open for just some more time. Okay. This is at minus 70 millivolt, and if it remains open, what do you think happens? Okay. This more potassium ions continue going outside. More potassium ions continue going outside, and minus, 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 minus. All right. And if you consider the profile right here, it goes down below minus 70 millivolt. Okay, it goes down till here. Now let us consider this value as, let's give an arbitrary value to that. Let's say it's minus 90. All right, I'll make it a dotted line as well. Okay, this is uh, this is the blue, yeah, minus 90 millivolt. Okay, then once it reaches around minus 90 millivolt, then I need to draw one more right here. Okay, this is in red, the potassium channel. What happens now is that the slow gate closes. The slow gate closes. Now it's a dead end for the rest of the potassium. It's a dead end right there. It's a cross. Okay, the potassium cannot leave anymore, and this is at minus 90 millivolt. So it stays there. All right. Now what happens? The last piece of the puzzle is that there's the sodium potassium ATPase pump right there, right? The sodium potassium ATPase pump right here. And what it does, since it's got very few, it's got fewer K plus inside now than there was initially. It brings in two K plus and throws out 3 Na plus, and it restores the polarity of the cell, the polarization of the cell, and brings it back to minus 70 as it was initially. Okay, and brings it back to minus 70. So this is one complete cycle. This from here, this is one complete cycle. All right, from here till back here. I'll make that dotted as well. Okay, this is one complete cycle, and this has a very nice name to it. This is called the action potential. All right, now we are coming to the good part, right? And each of these steps has a very nice name, have very nice names themselves as well. Now, since this is initially polarized, right? This is polarized, and here in this sort of ascending part, you see it loses the polarization a bit, doesn't it? It's minus 70, it goes to 0, then goes to plus 10. So it's losing the polarization, isn't it? So that's why this step is called depolarization. Depolarization means losing its polarization. Losing its polarization. And this step right here is called repolarization. The descending part of the graph of the sketch is called repolarization. Can you tell me why that is? Because it went to 0, it went to plus 10, it got depolarized. Now it's going back to minus 70, it's going to minus 90 in fact. It's going back to that value, isn't it? So it's getting polarized again. So that's why this is known as repolarization. And this little part of the graph right here, where it goes from minus 70 to minus 90 because of the lethargy, because of the slackness of the potassium voltage gated channel, this little part right there is called hyperpolarization. It's not called happiness. This little part of my life is called happiness. No, this little part of my life is called hyperpolarization. Okay, and then it goes back to minus 70. We don't really have a name for that, but yeah, It's really nice, isn't it? Once you get to know the meaning of these terms, it's not just a bunch of jargon, a bunch of mumbo jumbo anymore, right? You see, if you see depolarization, repolarization, hyperpolarization in a book, you'll think, like, what is this? What is this? Why these names? Why do we call them this? But now, once you got to know the meaning of these words, you get to understand, right? What was the mindset of those guys? Sure, they could have used maybe smaller words, but that's not really the point, is it? It's just to know that these words have meaning, and once you know that these words have meaning, it becomes all the more easier for you to understand, right? It becomes all the more easier to understand. It becomes like you can retain it in your memory for longer, and this way it's a win-win for all, isn't it? Okay, so now let's go to the next slide. Uh, this was the part about the generation of the nerve impulse. Once the action potential is reached, you say that an impulse is generated. Okay, so in the next slide, let's talk about the conduction of nerve impulse. Okay, now we are talking about the next part of the video, which is the conduction of nerve impulse. Okay, conduction of impulse. And now let's draw something. This is the real part of the video, right? I can sense the excitement in your faces. I can see I can feel what you're thinking, man. This is the good stuff. I can see Medusa head right there. I can see the tentacles right there. What do they call them? They call them dendrites, right? And this body right here. What is it called? It's called the cyton, right? This is a nerve cell. This is what we're talking about. This is what this whole video is about, man. What were you going on about? What were you going on with those foolish those schematic diagrams and all? This is the good stuff. Why couldn't you have given it to us sooner? But I couldn't have given it to you sooner because then you wouldn't have learned the basics, right? This is a nerve cell. This is the real stuff. This is a neuron. Now, I'm not drawing, in case you've already seen a nerve cell in some, in your diagrams, your book diagrams, you'll probably know that there's a myelin sheath in some nerve cells called myelinated neurons. But I'm not drawing that right now because it's not required. And maybe make some of the Nissels granules as well. Okay. Okay. So this is the nerve cell. Let's label out some of the parts right here. These are dendrites. This is the cyton. This is the nucleus. And this is the axon. And this little part right here is called the axon hillock. And these are the axon terminals, right? Okay, so now why do you think I label the axon hillock? It's just a part of the axon, right? Well, no, it's a very important part, in fact, because that is where the most number of sodium and potassium voltage gated ion channels are present. All right, so the axon hillock, it has the maximum number of sodium, potassium, all those different kinds of ion channels. All right, these are all these are all the different kinds of ion channels. So axon hillock has max number of Na plus and K plus voltage gated channels. All right. Okay, so this is where actually the nerve impulse originates in a neuron. It's not the cyton. Okay, it actually originates at the Axon Helix. All right. So let's see what we got going on here. Okay. Let's say the nerve. This is a part of the axon, and it's initially. Hang on a minute. I'll just do it below this diagram. Okay. Let's just say that this is the axon helix. I'm sorry about that. Okay. So initially, minus inside, and plus outside, right? You know why that is? Because of the resting membrane potential, right? The inside is minus 70. I mean, the potential difference is minus 70 between the inside and the outside, right? So the inside is negative compared to the outside, which is positive. So negative on the inside, positive on the outside. This is called the polarized state. Polarized state. Now let's draw it again. This is the same axon, part of the axon, and now it's getting depolarized. So it's plus on the inside and minus on the outside, but the entire part of the axon is not depolarized yet. It's partially depolarized, right? So plus on the outside in the remaining part, minus on the inside, on the on the interior part, right? So this is partially depolarized, right? Okay, now let's say the same part of the axon hillock, and now it's completely depolarized. All the positive charge is on the inside, and you know how the positive charge originates and the negative charge originates, we talked about in the last slide, and the negative charge is on the outside. So this is depolarized, or completely depolarized. You can call it completely depolarized or just depolarized, whatever. This is depolarized, right? Now we come to the next stage. This is still the axon hillock, just, or maybe any other part of the axon, whichever you like. Okay. Now it's getting repolarized. You know what repolarization is, right? The positive goes back on the outside in the first half of it, the one that got depolarized first, and the negative goes back on the inside. So you see the first part is repolarized, the second part hasn't. So it is partially repolarized. Right. And let me just number these diagrams. 1, 2, 3, 4. And now in the final diagram, I have the same part of the axon. And now it's completely repolarized. It's back to its initial state, initial polarized state. And plus on the outside, minus on the inside. This is number 5. This is repolarized. Alright, so we got that, and I want you to make a couple of inferences from these 5 pictures, right? Now look at picture number 2 and picture number 4, image number 4. All right, what does it seem? The positive charge it's getting depolarized. The axon is getting depolarized first towards the left, right? Now consider that this is the side of the cyton. Consider that this is 2 cyton, right? It's getting depolarized. The positive charge is coming on the inside first towards the left, right? This is where the positive charge is inside the cell. And now after some time, all the positive charge is towards the right of the cell, towards the right of the axon, right? And this is 2 axon terminals. So all the positive charge. So what does it look like? Doesn't it look like the positive charge inside the cell is migrating? I'll change the color. Is migrating towards the axon terminals. Doesn't it look like that? Migrating towards axon terminals. I think you can see where I'm going with this. This is how the nerve impulse is conducted, right? First, the axon hillock gets depolarized, then the adjacent part gets depolarized, then the adjacent part, then the adjacent part. So essentially, the positive charge on the inside of the cell keeps on migrating from the left to the right of the cell, right? From the left to the right of the cell. The positive charge keeps on migrating from the left to the right of the cell. And now I can go back to my previous diagram and say that if the positive charge arose on the inside of the cell right here, it will keep on going through the axon, the depolarization. It's called a wave of depolarization, right? And it will keep on going till it reaches the axon terminal, right? This is how the nerve impulse is conducted. You may think of it as electricity, but it's not electricity, all right? It's not electricity because even though it involves ionic movement, it's not ionic movement in the direction of flow of the impulse, right? Because the ions are just coming into the cells through the ion channels, going out through the ion channels, and that's how the charges that's how the charges are like sort of delineating themselves, right? So that is how the impulse is transmitted. It's not electricity, even though we kind of feel compelled to think of it that way, but that's fine. And That's basically the crux of the matter, right? And from the axon hillock, the impulse travels to the axon terminals, and once it reaches the axon terminals, there's a plethora of activities going on there as well, which we'll talk about in the next slide. Okay, so now we're talking about a very important bit called neurotransmitters. Neurotransmitters. Okay, neurotransmitters are a very important bit. All right, let's enlarge a part of the axon terminal. Okay, this is the axon terminal, and what's peculiar about this axon terminal is that there are small kind of like pouches, right? This is a pouch, this is a pouch, and this is a pouch. Okay, and these are filled with tiny molecules, with tiny compounds. Okay, and all of these parts, as you know, everything in biology has a name. So these pouches, they are called vesicles, and these little black molecules, they are neurotransmitters. Now I'll just talk about one neurotransmitter here, the most common that you'll encounter, called acetylcholine. There are a number of neurotransmitters like gamma aminobutyric acid or GABA, that's a neurotransmitter. Glutamine is a neurotransmitter. Um, Even adrenaline, epinephrine is a neurotransmitter. But let's just talk about about acetylcholine right here. Okay. So what happens? Have you heard of synapses? Since I'm making this video, let's get the basics right. Let's do it from the beginning. Let's do it the right way. Okay. So synapse is nothing but the gap between two adjacent nerves, right? This is the axon terminal. This is the axon terminal, and this is the dendrite of the adjacent nerve, right? And they are separated by a gap in between, and this is called the synaptic cleft. Okay, so now let's say our wave of depolarization has reached the axon terminal. Now once it reaches the axon terminal, I'll just make a couple more cuts in the axon terminal right here and insert a few more ion channels in that. Okay, let's make it blue. This is also a voltage gated ion channel, and the difference is that it lets in calcium ions, Ca2 plus voltage. Gated channels. Alright, so once the wave of depolarization hits the terminal, these gates open. These gates open. Now I've got these open gates, and the calcium ions, let's say that's in, let's make it pink. The calcium ions that were more on the outside of the cell, the calcium ions, that's a fact, know that for a fact, the calcium ions are more on the outside of the cell. They keep coming into the cell. Calcium influx, and I'll just make one really large vesicle right here, filled with the neurotransmitter acetylcholine. This is filled with the neurotransmitter acetylcholine, and what happens now is that the calcium ions, they bind to the vesicle and carry it to the membrane of the axon terminal. They bind. It's a complex mechanism, but they bind to the vesicle and carry it to the axon, to the membrane of the axon terminal. And I'll rub that out right here. And the vesicle has been carried to the membrane. All right, the vesicle has been carried to the membrane through the agency of the calcium ions. And what happens when the vesicle has a membrane of itself, right? And it's come in contact with the membrane of the axon terminal. And what happens when two membranes fuse? It just opens, spilling its contents to the outside. It just opens up. And what happens is these neurotransmitters that were inside the vesicle, safely inside the cell, they just get out into the synaptic cleft. Master gave Dobby a sock, Dobby is free. Master gave the vesicle a calcium ion, acetylcholine is free. Okay? Yeah. Okay, now let's say I'm inserting a couple more ion channels. Ion channels are everywhere, isn't it? They're like the backbone of this entire story. And I know I told you that ligand-gated channels won't be that important in our discussion, but it turns out I was wrong. It feels good when the teacher is wrong, right? The ligand-gated ion channels are also important. This is a channel. It has a space for the ligand here, and the ligand in this case is the acetylcholine, and it's gated. Okay, so I'll make just another one right here. It has a space for the ligand and a gate. All right, so what happens is the acetylcholine fits into this ligand. The acetylcholine fits into this ligand. I'm sorry, the acetylcholine acts as a ligand, and it fits into this receptor right here, into this receptor which is the ligand-gated ion channel. And what happens then is that this gate opens. It causes a conformational change, and this gate opens up right away. And then there's a lot of sodium ions on the outside, right? There's a lot of sodium, Na plus. Since this gate opens, this is a ligand gated. It turns out that this is a ligand gated Na plus channel. And what happens to the sodium ions is that they just keep getting in, and this causes sodium influx. And as you know, sodium influx of course leads to an action potential, and the impulse is conducted through the next nerve. Alright, so that's how nerve impulse conduction takes place, and I think that was the scope of our video today, and I think I've achieved that. So I'll see you later. For now, thanks for watching.